Okay, I've been asked to do a problem, a titration problem, where we are taking that titration to equivalence. Okay, and what that means is that the number of moles of strong base, which we have here, which we're adding, is going to consume the exact number of moles of the weak acid, in this case HClO, so that there is going to be no more KOH left in the solution, and there is going to be no more HClO. They've all been converted into products. And so when we look at titrations, here's a beaker, let's say, and we have here in this beaker a certain amount of this HClO. Then if you remember from the lab, a lot of times we'll put our base or our acid up here in a burette, and we'll just sort of start dripping our base, in this case, into this acid. And so we put an indicator in there so that that very last drop will then switch that indicator color, telling us that we have reached and actually surpassed slightly that equivalence point. Okay, so we want to know the volume that we've added, so we're adding new volume here to our beaker, and the chemistry that's going on is that we're taking this weak acid, this HClO, plus our base, and what we're generating from that in this neutralization reaction is we are generating this ClO minus plus some K plus we're making water. Now we know by now that this aqueous ClO minus is actually the conjugate base of a weak acid. And so since this is a base, it is going to react with water. ClO minus plus water is then going to produce an equilibrium here of HClO plus, we're going to generate these hydroxide ions. And those hydroxide ions are basic, and they're going to raise that pH above 7. So at neutralization, then our pH, because it has a conjugate base that is being generated here, is actually going to be greater than 7. It's not going to be a neutral pH. And so at the end of our titration, floating around in here are not going to be any KOHs, is not going to be a strong acid. We're only going to have floating around in there. Is the ClO minus as a weak base. Okay, that's what we're going to have floating around. This is going to be negligible. And we're going to have these hydroxide ions that are going to be generated. And so we need to do the math to account for this. Okay, so let's do this math. And so I start off with 250 milliliters, but I'm going to hurry and convert that to liters in my head. That's an easy one. Okay, this is 200.250 liters of this HClO. Okay, I'm going to react. I'm going to convert that into moles using the molarity. So I know that in 1 liter of that HClO, that there are 0.5637 moles. I'm just using what's been given to me right here for that HClO. Okay, that's the amount of here before I've added any KOH. I then add the KOH. Okay, and when I add that KOH, I know that for every 1 mole of HClO, I want to make sure my units of HClO cancel out here, that I am going to consume 1 mole of KOH. This is going to tell me the number of moles of KOH that's going to take to neutralize this volume and concentration of HClO. But notice too that since this is a 1-to-1 stoichiometric relationship, that this is also going to tell me the number of moles of ClO minus that I am going to generate. Okay, so the number of moles of KOH as well as the number of moles of ClO minus that I'm going to generate is going to be given to me from this math right here. And when I do that, then I calculate that I get 0.140925 moles. That's of the KOH that I've added that's being consumed, and that's the moles of ClO minus that are being generated. Okay, but I also need to account for all that volume that I've added, because that's going to change my concentration because I'm adding volume here. And so I can do that by continuing on in this math right here, because I know that there are 0.3981 moles of KOH for every liter. And so I get that just by using what's given me right here. And so now my moles of KOH will cancel out. And so the volume of NaOH that I've added, I calculate to be 0.35399 liters of KOH that I've added. Now that's only this amount right here. I need to account for all that volume. So I'm just going to add it to the original 250 milliliters, or 0.2550 liters. And when I do that math, then I get that this new volume is 0.60399 liters. Okay, so I can calculate a new molarity of ClO minus that I have in there. Remember, there is no more KOH. There is no more HClO. There is only the ClO minus that's going to function as that weak base. And so I can then take my new volume, divide by that new volume, and that will give me moles per liter of the ClO minus that is in this beaker right now. And when I do that, then my new molarity of ClO minus is 0.2333 molar, or moles per liter. That's the new volume of ClO minus. Well, now I need to account for this chemistry right here, where I'm generating those OH minus ions. Okay, and so I can do that then by making my ice table. And so I have an ice table here. Okay, and notice also that I am given a pKa of this solution. So I can use that pKa. Okay, so I know that the pKa equals 7.50. Okay, but this is the base. This is the conjugate base of this hypochlorous acid. So I need to come up with the pKb. So the pKb equals 14 minus the 7.50, which is the new pKb equals 6.50. Okay, and now I can calculate a Kb, which is going to equal to 10 raised to the minus 6.50, and so my Kb is going to equal 3.16 to 2 times 10 to the negative 7th. Okay, so I calculated a Kb just from what was given me, and we know that we can write a Kb reaction for this guy right here by saying that the Kb equals concentration of HClO, concentration of OH minus, divided by the concentration of the ClO minus. Okay, so I can use this Kb, and we've done a ton of these problems from this point on. This should be real easy for you guys to do. Okay, so we'll make this ice table based upon understanding this Kb equation right here. And so I'm going to have ClO minus, I'm going to have the HClO aqueous, and I'm going to have the OH minus in here. Okay, so I already calculated my initial concentration of ClO minus, which is 0.2333. I'm not going to have any of this initially. Then some of this is going to go to the right of this equation, and so I'm going to have how much? A minus x. We'll just call that x. This is going to be x that's being generated, and x, just an unknown variable. Okay, and so at equilibrium, I'm going to have 0.2333 minus x. For the ClO minus, I'm going to have x, and I'm going to have x at equilibrium. Okay, so now I can substitute these into my Kb equation, and I can just write that Kb that I calculated, which is 3.6122 times 10 to the negative 7th, is going to equal x times x divided by 0.2333 minus x. Okay, now because our Kb is really small, then we're just going to assume that I can ignore any addition or minuses to this value. It's just not going to change anything at all. It's like having $1 billion and adding one more dollar to that. It doesn't change your net worth by anything of significance at all. Okay, so I can now solve this just algebraically, right? I have x squared divided by 0.233. I'll multiply, I'll take this over, and so when you do the algebra, I'm not going to do it for you, you can get that x equals 2.71639 times 10 to the minus 4th. Okay, so that's, I solved for my x. Well, x is the concentration of the hydroxide ion. So from here, I can calculate I can do this a number of ways, but I can go that the POH equals minus the log of the hydroxide ion concentration. That's the definition. So minus the log of 2.71639 times 10 to the minus 4th. Okay, and when I do that, then I get that the POH equals 3.566. And so it's not asking for the POH, it's asking for the pH, and the pH is going to equal 14 minus the POH, which in this case is going to equal 10.43, and I'm going to answer that to 2 decimal places. So these can be a little bit long, and you have to keep track of what's going on. I just did this titration little diagram so that you can understand that we're adding volume, so you need to account for that adding volume. We're consuming all of the HClO, we're consuming all of the KOH, and we're generating the ClO minus. This is a very simple stoichiometric problem that we can do. Okay, so I stop right here. This will give me my moles of KOH that are being consumed, and that will generate also the number of moles of ClO minus. I take this equation just a little bit further so I can get the volume of the KOH that I've added right here, and then I'll just add that to what I had originally in there of the HClO to give me my total volume. Then I'll just take the number of moles that I calculate divided by the volume to get me a new molarity. And once I get that new molarity, you need to understand that this chemistry right here is going on. And you guys have done a ton of these where we do these really simple ice tables, and then we can solve for x. maybe one thing that, not tricky, but you just have to realize is that you need to write a KB expression for this, and you need to calculate the KB. If you're given the pKa, you should be able to calculate many things from that, but among those you should be able to generate the KB from that, and I showed you how to do that. A simple ice table and just some simple calculations. So it's just keeping track in your mind of everything that you need to do. They can be busy. I don't think they're hard once you understand the chemistry going on, but they're busy, and there's lots of areas to make little mistakes in. And so just carefully go through these, understand the chemistry, do some stoichiometry up front, do a very, very simple ice table, write a KB expression that accurately reflects the chemistry going on, and then do the basic algebra that you need to do, understanding that when you get X, that X was the OH concentration, and you can imagine problems where you're actually figuring that out. Instead of for a weak base, you're doing that, a weak conjugate base, you're doing that for a weak conjugate acid, and that would actually be a little simpler than what we're doing right here. But know that from that you can calculate a pOH. Once you get a pOH, it's very easy to get a pH, and that's how you would do an equivalence problem.